Okay, thank you very much, everyone. And I'd like to introduce Adam Lowdon, who's going to give us a talk this lunchtime as part of our DEI CDT seminars on offshore wind, the security and risk. Alan has had a long industrious career, but probably for us at Durham is our professor in practice at Durham Energy Institute, and has actually been a great supporter since the inception of Durham Energy Institute itself, and has also been chair of the advisory board as well for several years. So yes. Over to you, Alan. Thank you very much.
Thank you very much, Stuart. Welcome everybody online and in the room. Hopefully you'll find this slightly different, a bit of an insight into some of the emerging issues in the offshore wind industry related to security and risk. These are mainly personal perceptions, personal interpretations of what's happening. There's not much in the literature on this, but I'm sure there will be in the future as it starts to become really important. Okay, so what we're going to do, we're going to look at a little bit of scene setting. We'll talk a little bit about the offshore wind system. Why is risk such an issue in offshore wind? And where is it? Which is important. We need to identify it. And of course, how do we mitigate it? So let's set the scene a little bit. So two takeaway messages for the audience, which I tend to bang this drum quite a lot these days. Offshore wind science, technology and engineering are inextricably linked to offshore wind finance, economics and insurance. Now, underpinning all of that, of course, is risk management. There's a common factor in all of that. We'll pick that apart as we go through the next 45 minutes or so. And also, as students and future industrial practitioners or commercial practitioners, being able to see the industry through the lens of risk and risk management is a huge personal differentiator. It's one of the things which I say to students when I speak to them, say to people who are in their early careers, if you can append your technical knowledge with the knowledge of finance, risk management, the softer skills as well, you become quite an employable individual. So there's nothing better than in an interview if somebody is talking technical and they suddenly switch to talking about the bottom line impact of that technology or of that particular asset class, be it offshore wind or solar, tidal, whatever the technology is. So yeah, so those are the two takeaway messages. So have them in the back of your mind as you go through this presentation with me. So why is risk such an issue in this industry, this emerging industry? So the first mental model, which I think is important to grasp, is this so-termed bathtub curve. Now this applies to any infrastructure asset. So effectively what this is telling you is that when you commission an asset, there's a period where you have to run it in to get its optimal performance so that the machinery or the control systems or whatever is actually operating the asset become attuned to that asset's performance and operated optimally. So that means that the costs drop over time until you achieve this optimal performance. So that's the run-in phase. Then you sustain that operation for a period of time at that optimal cost point. And then as things start to wear out and have to be replaced, you start to see that cost curve start to move up again. And the trick, of course, is to push that second turning point out as far into the future as you can because of the time value of money. And ultimately, the assets, even though they're maintained and parts are replaced, etc., they do reach the end of their life and have to be repurposed. So this is the underlying sort of construct around any infrastructure sector. And we're talking about offshore wind here, but it could be anything. It could be combined cycle gas turbines, it could be general power stations, it could be motorways, it could be factories, whatever it is, whatever asset class we're talking about needs to be dealt with like that. And of course, all of this is subject to these externalities which arise periodically, and we'll touch upon some of them. So have that in the back of your mind. So the production system in offshore wind, simplifying it considerably, there is the nacelle, which is the bit which sticks out of the back of the turbine. There's the tower, which is the bit that keeps the turbine in the sky. There are the foundations. Now, those foundations can be in the ocean, in offshore wind, or they can be on land, in the case of onshore wind. There's a substation, which, if the turbines are far enough out in the ocean, then you need a substation to gather the electrons and transmit them back to shore in an efficient way. You've got the cabling. So the cabling are these myriad of connectors which connect the turbines in the arrays. So this particular diagram here, underneath the ocean wave, you will have a myriad of cables which are connecting the turbines together. And then you'll have what's called export cables, which are taking the electrons back to shore. And of course, you've got the ancillaries, which are the various other bits of pieces which make up the turbine system. So that could be the inside of the nacelle, there's control systems, there's gearboxes, there's all kinds of things going on. And of course, I haven't mentioned the blades. The blades are really important, and I'll come on to that a little bit later. So there's visible assets on the surface, and there's invisible assets underneath the waterline. And it's those invisible assets which create a lot of the risk. I'll come on to that. These are called asset classes. That's a terminology which you may have come across, but or components. But in investment speak, they're called asset classes. And so, a little bit more detail. So, when you are actually constructing an offshore wind farm, as per this diagram, this photograph here, you actually have what's called a jack-up vessel, which basically has feet which sit on the seabed, and it heightens itself or lowers itself in relation to what it's constructing. Here is the turbine going into the water. So you can imagine there's a limit to when these technologies can be used because of the water depth. There's also the operations and maintenance. Once the turbines have been constructed, the further out to sea you go, the more complex that becomes. And helicopter operations and maintenance operations in far-flung wind farms 100 miles offshore is becoming more commonplace. The other challenge is the design of the turbine system, how it's laid out, and how much you get from it once you've laid it out, how many electrons you get from it. So this is really important. As a fluid dynamicist, I like this diagram because it shows you what not to do. Here you've got an array of turbines. This is called Horns Rev wind farm off the coast of Denmark. And if you look closely, you've got the upstream, the incident line of turbines here, and then you've got this wake which is being produced. And if you look carefully on this photograph, you can see the other turbines which sit behind there. So you can see this flow which is impinging upon these turbines is far from regular. It's turbulent. Turbulent flow has a lot of energy in it. As you know, when you hit turbulence in an aircraft, you know about it. So these turbines downstream of this wake receive all manner of different loadings from that incident flow. And that can cause accelerated aging. It can cause failures. So it's really important to design your turbine system with the correct layout. This was an early wind farm that was basically designed incorrectly, and there's been a lot of maintenance required on those turbines. I mentioned before the power export aspect, and the cabling is the key arteries. You can have the best turbines in the world with the most efficient blades, the most rigid tower, but if your cables fail, then the electrons have got nowhere to go. So the cabling is extremely important. And about 70% of insurance claims related to offshore wind in the City of London relate to cable failure. So that's a big cost component of any offshore wind farm development. So, I mean, I won't go this because we haven't got really the numbers to do this properly, but anybody want to have a go at what kind of risks that you perceive before I start delving into them, which exist in an offshore wind farm? Feel free to shout out.
I think the most important one is the logistics. That you have to travel hundreds, maybe, kilometers into the wind turbine in bad weather. So that's a big issue.
Logistics is a key one, yeah. Any others? Oh, Stuart, you must have a one.
C4 geology.
Right, okay, you've gone technical straight away. Yeah, well, that is a risk. These things tend to be looked at. Well, certainly the bathymetry of the site is something which gets a lot of attention before an investment decision is finalised. But yes, you're right. Anything else? One more? Yep, climate change. The incident flow that the turbine receives can be variable and unpredictable, and that is a massive thing which is going on, and I'll talk about that in a little bit in a moment. Good. So let's have a look at some of the others. So technical risks. We've already talked about the wrong design of a turbine layout, so that's a huge risk. The construction. You know, if you start constructing in a nice weather window and the weather changes, you have a huge risk. What do? You have to stop. Of course, you have to stop from health and safety point of view, but you've got a vessel on hire, which is it's about $200,000 a day. You know, it's not cheap, so you've got something to do. You've got to take decisions. Operationally, you've got equipment reliability if the weather changes, like you said. The maintenance regimes that you have to be fit for purpose, because if they're not, there's a risk that the assets won't perform as they should to give you the commercial return that you need. And of course, extreme weather events, we don't have that many in the UK, but I'm heavily involved, as you saw on the opening slide, in the United States, where we have a lot of hurricane risk, which we don't have here. So the design of the turbines has to be in line with the risk which is being either perceived or likely. So hurricane risk is a huge one, and that has an impact upon the design of the blades, the tower, how you operate it. You can have to bring the blades in, called feathering, if the incident flow is too violent. So all of these are huge technical risks. Financial risks, upfront investment. You know, to get something going, you have to commit, you have to find the money, you have to apportion the money at the right time. Of course, nothing ever goes according to plan, so there's always cost overruns, so you have to provision for them. Delays in project completion because of things like weather windows, things like component parts not being available for whatever reason. Fluctuations in energy prices. There's a thing called the final investment decision, which is taken before a wind farm is finally okay to be constructed, and that final investment decision takes all of the factors known and predicted into consideration when setting the budget for the job to be done. And part of that is how much you're going to get for the energy when you actually start generating it, the electrons. That can change. Right, where was I? Right, so yeah, fluctuations in energy prices can be a big impacting factor. Power purchase agreements those are the deals which are struck to give these final investment decisions a nudge over the line usually. And of course, you need to have government incentives and policies which allow long-term investment decision making to take place. So you need forward visibility of government policy, i.e. consistent policy, which is going to underpin the industry. And I'll come on to a little bit later, the levelized cost of energy and the impact on that parameter of certain things that you do from a risk point of view. Obviously, environmental risks exist as well. And the disruption to marine ecosystems needs to be mitigated. Noise pollution is one of the things which people always latch onto, and incorrectly in many ways. Impact on ocean stakeholders, that's the fishing community usually. The shipping lanes need to be either rerouted, or they need to be, the risk needs to be mitigated in a different way. And of course, the Navy, they always have their national security interests to look after. Technical risks, as I've said before, this is just a repeat of that one. I don't know why it's in, but we've done that. Regulatory risks, as Ben, what you said, the permitting and consenting timelines, they're really important. There's a big move in the market now to go for what's termed rapid permitting. So how can we use technology to allow us to understand the impact on the ocean environment of the construction of an offshore wind farm? The longer you take to permit or consent, permitting is the US phrase, consenting is the UK phrase, the longer you take to do that, the longer it is before you start getting your return on investment. So everybody wants the permitting process to be shortened, and they want existing data sets to be used in a more strategic way, i.e. not repeating the same data gathering exercises each and every time you put a wind farm up in a similar location. Changing in environmental laws, that can be a big impact between the idea to put a wind farm up somewhere and the reality of its construction. Things can change. Licensing requirements is another one in terms of the way that the ocean is permitted. The licensing in the UK, it's the Crown Estate. In the United States, it's the Bureau of Ocean Energy Management, who gives the developer the right to site an offshore wind farm in a particular footprint of ocean. So that's the licensing. And also government support schemes, they change. In the UK, when offshore wind started to become a serious asset class, the government was subsidising the industry, and the levelized cost of energy, which I'll come on to, was around about £180 per megawatt hour. It's now dropped to of the order of 50. And that's all in 10 years. And that's done because supply chains have matured, incentives are no longer required, there's confidence in the industry, and people have invested to get that continuity and that value chain established to go from permitting through to operations and maintenance, and ultimately to either repowering or decommissioning. And regulatory schemes always depend upon politics. So there will be a change in policy as a result of a change in government, not necessarily a wholesale change, but there could be tweaking of the particular instruments which are in place from a regulatory point of view. Supply chain risks, the complexity of the supply chain. You've seen typical activities which go on in a wind farm in terms of the cables, the nacelles, the towers and everything like that. But that all requires materials to be in existence, components to be in existence to allow that system to be assembled. And these supply chains can be disrupted due to global factors. And we've seen that over the last 2 years with the Ukraine crisis, and it'll continue to change as things become, as adaptations to the supply chain out of necessity occur. Delivery delays, ships getting stuck in the Suez Canal doesn't help. When things like this are so reliant upon small components such as circuitry, circuit boards, electronics, not big assets, but important assets. And also quality assurance in terms of the supply chain. Components, steel quality is really important because clearly you're relying on the quality of the steel to keep the turbine erect in the ocean. So you want to make sure that the steel is up to the appropriate level of quality, and this is all standardized. And of course, project management, the construction of the wind farm needs to be overseen by professional project managers, and they come in terms of their key element of the supply chain because they come with the expectation that it will be delivered to time, cost, and also to quality. Stakeholder risks. These are really quite significant. Local communities become quite scared often of the arrival of the offshore wind industry in their region. Why? Because it can actually disrupt existing activities, but it can also create new economic value. So when they become engaged, and I've seen this in the UK, I've seen it in the US, seen it elsewhere, once they become engaged and understand what they're dealing with, often the economic value far, far outweighs any concerns that they've ever had. Government agencies, they change, people come and go. It's a risk because you're dealing with one person one week and another the next, and that continuity of messaging, continuity of influence is important. Investors, the investors are, if anything, the most flighty of any of the key stakeholders, because they are the ones who can turn off the tap with regards to funding, or they can turn it on as well. So keeping them sweet is extremely important, and keeping them appraised and keeping them up to date with technological developments, as well as their financial and risk around their particular investments, is really important too. So we have environmental groups as well, key stakeholders who will monitor and see what's going on in the farms and ensure that their own interests are reflected in the activities underway. Sometimes you have conflicts of interest. You can have, for example, the airports are a prime example where they stand to benefit significantly by the influx of people into a region through greater traffic in the airport, yet they can be conflicted because the offshore wind farms can interfere with radar. So we saw this, and I'll finish, one of my last slides is showing you a little bit about a demonstrator up the road at Blythe. When we pulled that together many years ago, about 12 years ago, Newcastle Airport was the key stakeholder that we had to convince to allow that to happen, because it was on the turning circle into the runway over the North Sea. And we did that by helping them to upgrade their radar. So they were very, very appreciative of that, and it's subsequently proven to be a very good decision. And the biggest opposition, and this is global, not just here, it's been and gone here, it's global. Everywhere the offshore wind industry rides into town, the fishing community usually have their hands held high out of potential despair, thinking it's going to wreck their industry. And of course, guess what? It never does. So fish love offshore wind farms. They provide safe havens for them to breed, for them to congregate, for them to spawn. They love offshore wind farms. And you can't trawl within the offshore wind farm. You can't trawl within the channels between the turbines, but you certainly can't trawl around the turbines. So fish, would you believe, actually live in the base of turbines. Artificial reefs are created, which they feed off, and they provide a habitat. And now the first wave of early offshore wind farms in the UK could well be replaced. And there's people are up in arms now because you're going to affect the artificial reefs which have been created for the fish. So things go a full circle. The other thing as well is reputational damage, which can occur if the developers and the stakeholders don't come together and find middle ground to develop these farms. Reputational damage can be apportioned both ways, so we try to avoid that. So stakeholder risks are really important. But it wasn't all about all of that. I'm more interested in this emerging stuff around security. So let's look at physical security. So now think what you've seen in the pictures. You've seen assets in the ocean, typically a wind turbine which is fixed to the bottom of the seabed will be in approximately 25 to 40 meters of water depth. So it's quite a lot of water between what you see and what is going on the seabed. So anything can happen, i.e. the assets could be subject to vandalism. You know, anybody in a boat can go out and do something to those turbines because they're not physically protected 24/7. Sabotage through submarine activity, and anybody who has unauthorized access could, in theory, get in a boat, go to the turbine, step onto the turbine, because I have little gantries which the crew transfer vessels are designed to come up against, get onto a turbine and do some damage. So this is a concern. So we can mitigate the risk with physical security, fences, surveillance cameras, access control, etc., and security patrols. So this is the same for any asset that you'd be constructing. There's also the cybersecurity risks, which you'll see in a subsequent slides. The amount of data management which goes on in an offshore wind farm now is extremely high. Data on the performance of the assets is happening all of the time, and that data has to go somewhere. You're controlling the assets. We could control an offshore wind farm sitting here in this classroom now, 100 miles offshore, because of the SCADA systems which are in place, and because of the smart, intelligent assets that we're producing out in the ocean with embedded sensors. So digital technologies and communications are instrumental in this industry. They are subject to hacking, malware, and data breaches like anything else. So that needs to be mitigated. So we have encryption, we have firewalls, we have all the normal stuff that you would see in any computer system. And also, importantly, this is where the industry is heading, intrusion detection systems and security protocols are starting to become really important in terms of cybersecurity as well as physical security. So typically, an offshore wind farm would be wanting to do something like the dotted ellipse at the top. You would be generating data to create information about the asset's performance, to give you some knowledge about what was going on, and then to get some wisdom over time as to how that particular type of asset would be performing. So what we have here is we have all of this remote sensing and imaging coming from the asset. It gives you asset performance insights. You start to get a little bit of a feel for how risky these assets are. By getting all of this data in one place, we contribute to the knowledge about the industry and over time, the performance of particular turbines or particular turbine systems that allows you to improve your planning for the next wave. So there's a huge feedback loop created here. And this all takes place, I'll come on to the diagram in a moment on the next slide. This all takes place in what we tend to call an offshore wind data hub, which is land-based. So you beam back the information to those places. But by getting the information in a particular form, going through that process at the top, from data to wisdom transformation, you become more optimal in your intervention rates on the assets. You can actually maintain them in a more cost-effective and timely way. You reduce risk. You create greater certainty about what you're likely to get out of those assets, which makes them more investable. And that in its own right has a massive impact on the levelized cost of energy, which I'm going to talk about in a moment. But this is the schematic of what I was just saying. You've got offshore wind farms, offshore wind assets, offshore wind turbines, which are generating data on their own individual performance. And that goes back to this land-based offshore wind hub, where all of the stuff goes on: capture, analysis, decision support, optimization, and also intellectual property development. Because what you want is, if you're doing this smart, you want to be able to take what you find, create feedback loops, and start influencing the design of the turbine so that their performance improves over time. And from a mathematical point of view, for those interested, this is effectively one huge constrained optimization problem. There are two other factors which is beyond today's discussion, but we could certainly pick it up in a future lecture. Is the importance of in-warranty versus out-of-warranty activities and responsibilities of the original equipment manufacturer. So typically a turbine, once constructed and commissioned, would be in warranty for a period of around about 5 years. And the supplier would be responsible for maintaining it and making sure it was in line with what's termed the turbine supply agreement. Come the end of that period, then the asset owner who bought that turbine 5 years ago has responsibility, in theory, to continue that maintenance. So he or she, whoever's taking the decision, can either stick with the OEM and give them an extended warranty contract, like you do on the car, for example. They can bring that activity in-house so that they create their own maintenance teams, or they can outsource it to a third-party service provider. That decision is theirs. But of course, from the OEM's point of view, there's 5 years worth of data which is going to have to be handed across to the service provider, whoever that is. So there's two service providers who they don't want it to go to. The one service provider they want it to go to is to keep it themselves. So there's always this tension in the run-up to the warranty period expiring between the original equipment manufacturer and the asset owner. And it happens each and every time. So there's lots of discussions which ensue in the run-up to that handover point. So that all adds to the risk. That all adds to the perceived risk and also the actual risk as well. And looking at some maritime security risks, you know, the extreme and offshore location, often, as I said before, 100 miles over the horizon, makes offshore wind farms susceptible to piracy, maritime accidents, you know, ships hitting the turbines by mistake can happen. Look what happened in Baltimore. You know, that's an example of what can happen if you stray off course. Unauthorized vessel access. You know, it's a challenging situation. So we're starting to see the emergence of patrols, surface and subsurface patrols. Radar systems are becoming ever more sophisticated, so you can pick up things which are going on remotely on an asset and do something about it. AIS tracking, so basically using drones and stuff to track what's going on those assets periodically. Having in-situ mounted robots to actually inspect the assets to make sure that they're not being tampered with. And also restricted access zones, which actually, where one sets alarms, alerts around people intruding into them. So this is all adding to the cost of the industry out of necessity. We also need to have emergency response and contingency planning if any of this comes to pass. So we need to respond swiftly to any of these security incidents or operational incidents like a fire outbreak on a turbine. That's possible. We talked about mechanical parts, moving parts. There's electrics, which can actually spark and cause fires, lightning strikes on the turbine from external factors. Environmental factors, natural disasters. You can have an earthquake which moves a turbine or something, and the structure starts to become a little bit exposed to loading. So we had to coordinate with emergency services, so with Coast Guards, with fire services, with the Army, with the Navy. Training drills are really important, and training itself is really important. Down the road, it's not far from here at Hartlepool, there's a new global offshore wind training facility, which has just been opened about 3 weeks ago, which is specifically there to train technicians in how to evacuate a turbine in the event of fire. Advanced fire rescue training, really important in case it happens, and it does happen. So all of this is so important for the future safety of the people working on the turbines. And exercising of communications protocols, like any disaster management system, you need to have periodic, effectively periodic alerts, periodic training to make sure that your response is fit for purpose. So like your 11 o'clock every Wednesday morning fire alarm in a hotel going off. This is the type of thing that people would be wanting to do periodically to make sure that if something does happen, they're able to respond accordingly. We talked about the regulatory compliance side of things, but we're seeing security regulations starting to emerge, standards for the security aspect of construction, guidelines as to how government should behave and how international organizations should behave, because often these turbine systems, they butt up against different coastal zones and responsibilities. So the 12-mile limit around the United States, for example, is US Coast Guard territory. Then you get into international waters, etc. So you have to have some kind of system where the international organizations can play on the same field. And it's basically, the safe, reliable, and sustainable operation of the wind farms is really important. Again, we're mitigating the risks and protecting the assets and maintaining this phrase resilience of the infrastructure base in the face of security challenges. I've spelled challenges wrong. Yeah, so I mean, this is just a reiteration of what we've said about this operations and maintenance hub, bringing all this information into play around these different activities and these different asset classes. We can simulate this digitally now, of course, with the creation of digital twins. So I would say now, for those who are interested in the data side of this, there's as much activity in the industry on the digital side, the simulation, the modeling, all of the stuff which you need to do to see how a farm is likely to behave, see how it's likely, what it's likely to cost at the outset, so that you can plan accordingly. There's as much digital as there is physical. The civil engineering people are all digitally equipped. The mechanical engineering people are all digitally equipped. Electrical engineering, all digitally equipped. And so you can become quite sophisticated in how you construct and operate your asset base. So in terms of key techno-economic factors at play, because remember what I said at the beginning, if you can speak the language of technology and match it with the language of finance, then you're in a very strong position as an individual. You also have to have an appreciation of the intersection, the techno-economic impact of decision-making and risk factors that we've discussed. So we've talked, and I think we've belabored the point, we have to ensure that health and safety is of paramount importance at all times. Environmental compliance also, to keep the stakeholder groups on side. You have to maximize energy production so that the return on investment matches what you actually thought it was going to at the outset. And if it's starting to wander off, you have to do something about it. You have to reduce asset downtime, because that inextricably is linked with the previous point. The more time your assets are down, they're not producing electrons, which means you're not getting paid. You have to intervene in a timely manner when required to keep the assets turning. So the maintenance strategies have to be compliant. And we talked about the in-warranty versus out-of-warranty responses. And typically, the in-warranty period tends to have a longer lead time to response than the out-of-warranty period, if that out-of-warranty contract has gone to a third party. Why? Because they're incentivized to respond quicker. So that you can factor all these things into your contractual wording and the design of the contract, such that you're mitigating that risk at the beginning. And the purpose of this, and we talked about everything on the left, the risk which goes with all of that stuff on the left leads to what we term a higher levelized cost of energy. Now, why am I laboring this point? Because risk and levelized cost of energy are inextricably linked as well. So I want to talk a little bit about that in the run-up to finishing. Does anybody know what levelized cost of energy actually means? Online or in class? Right, good. Then I can define it. I can give you the equation. As a mathematician, I like an equation. Right, so it is the key parameter by which energy technologies are judged. See that in a moment. It's a reflection of the embedded risk in a development, the development being the wind farm in this case. It's a function of the asset class, i.e. onshore wind, offshore wind, combined cycle gas turbines, etc., all have different levelized costs of energy. It's also a function of of several identifiable and controllable factors, and we'll talk about in a minute. It's also a function of some stochastic or random factors, which are usually uncontrollable. It's asymptotic. Again, I like to weave another mathematical term in there, which means that you can keep trying to get it down, but it can never be zero. There's a line to which it tends. Now, what is that line? Nobody knows, because technology advances, but what it is, it's not zero. You cannot have a system which has zero levelized cost with it. It's rightly or wrongly the dominant logic which is sat alongside the offshore wind industry since it became into being, more so than other technologies, I would say, and I'll show you in a minute for why. In the US, which is why I put this line in, it's been sufficiently reduced to effectively kickstart the US offshore wind industry on the back of risk reduction, which has happened elsewhere in the world. So the US is coming into the offshore wind industry at a price point which is very attractive, because all the heavy lift to de-risk the industry has been taken in other markets, European markets, UK in particular. But levelized cost of energy is indeed volatile. It can go up as well as going down. So understanding the impact on it through the risk that you're actually managing out is extremely, extremely important. So here we are. Here's your equation. So levelized cost of energy equals, it's the life cycle cost of energy production in pounds or dollars, or whatever your currency is, divided by the life cycle energy generated. So over the lifetime of the asset, how much does it cost to produce the energy from that particular turbine or farm? You can do it on a micro basis, or you can do it on a macro basis. And how much energy is generated over the course of that asset's life. So for those of you who are interested in equations, you know, to make this number as big as possible, as small as possible, we want to reduce the levelized cost of energy. We don't want it to go up. Excuse me. To get that thing to remain and to be what's called monotonic decreasing, i.e. on the way down, we have to minimize the numerator, which is the thing on the top, at the same time as maximizing the denominator. So if you've got a small number on the top and a big number on the bottom, then this thing remains small. So your challenge as operators of wind farms, all of you here and online, is to reflect on how you actually do that. What do you do to minimize the cost of energy production based upon what we've already said? There's lots of factors in there which point to this, and at the same time maximize the amount of energy produced, because the more you get out, the cheaper the levelized cost of energy becomes. So you can see from this, the levelized cost of energy in terms of units is pounds per megawatt hour. So that's what we're dealing with, pounds per megawatt hour. So quite simply, what we do is we minimize the numerator. So to do that, to reduce the cost of energy production over the life cycle of the asset, which is typically 25 to 30 years, we optimize the operations and maintenance to make sure that the asset is running it for as long and as frequent as possible. And we do this via strategic asset management strategies. I used to run an elective on the MBA at business school here called strategic asset management until I was kicked off. But I did have the best scores out of any elective for 2 years. Yeah, but then...
Can I ask?
Yeah.
Can I ask a quick question about that? You said
Please.
the life cycle of wind farms is around 25 years, expected life cycle. I thought the jury was still out on that, because some of the assets that were built 20 plus years, the early onshore assets that were first built, are now exceeding their life cycles. And I wonder whether if you can tweak them so they last a lot longer, that's obviously going to impact on your levelized cost. Yeah. So I wonder whether, are we sure that it's 25 years, or is it still kind of we're waiting to see what the...
Well, you have to pick a number because the insurers want to have a number. So these assets are insured with a design life of 25 years. And that's what when you sign your turbine supply agreement, so you can go to Siemens tomorrow, for example, and say, I want to buy a turbine. They'll put a turbine supply agreement in front of you, and in that agreement, there will be a nominal design life of 25 years. Now, so you deal with that datum from the word go, and if you can extend that life, because think of that bathtub curve that I showed at the beginning, if you push that second turning point out far enough into the future, then the life cycle cost is reduced because time value of money and all of that. So that's why I put that graph up there, because that inextricably is linked with this. So if you can push your operating envelope such that you get another 5 years out of your machine, through good maintenance practices and keeping on top of it with smart asset management, then that's a good thing. And that will affect your levelized cost of energy, because you're doing the top, a world of good, the numerator, and the denominator, you're generating more power from that investment that you took 25 years ago. So yeah, good point. And so other things that they do to maximize the denominator, i.e. get more power out, is you use larger turbines. I'll come on that in a second, which give you greater yield. Yield is the amount of energy you get out of a turbine, and you have more resilient assets so that they don't fail. So larger turbines, okay? Typically when the offshore wind industry started, a large turbine was 2 megawatts, okay? And this is going back into the early 2000s, 2 megawatts. Now, remember that figure, 2 megawatts. We're now putting turbines, designing for turbines to go into the ocean of 15 megawatts. That's big. 18 megawatts is on the design board, drawing board in certain providers, but 15 is where we're more or less looking now at new developments starting to be populated with turbines of that size. Another factor, these blades on these turbines are huge. So a 15 megawatt machine would have a blade typically 120 to 130 meters long. Bigger than a football field. What's one blade? You imagine when you put them, so the rotor diameter was one pointing vertical and one pointing towards the ocean. You've got 250, 260 meter stretch from bottom of the tip of the bottom one to the top of the one pointing due north. Huge. The big factor here is if you double the length of a wind turbine blade, its power output goes up by a factor of 4. So you can see why developers want bigger turbines. Not only do they get more out of the turbine, i.e. because they're bigger rated, the megawatt rating is greater, so 15 megawatts as opposed to 2 megawatts, you're getting a lot more out. But if you make them more resilient, they go for longer. The greater yield because you've got these blades which double in length every few years. So the power output goes up by a factor of 4. But there is a limit. There's another asymptote to which this is going to tend, because the logistics of construction become prohibitive. The vessel size is required to actually move these things from port to the point of construction, or you change the game by assembling in port and floating out. That's another thing that's happening. That's another hour in its own right. But suffice to say that this is a simple equation, but it looks simple. It's not quite as linear as it looks. It's quite non-linear. But in your own mind, that's what's driving the industry to continue to keep this cost in check by doing the things on the top and on the bottom of that equation. So just to give you some figures as to what makes up the capital expenditure element of the levelized cost of energy, which is the construction cost. You can see the split there. So project financing, the cost of the turbine, the cost of logistics and installation, the foundation, the services and electrical infrastructure, all comprise are key components of that overall cost. But and also the mentioned before, the cost of money, the project financing accounts for around about 12% of the capital expenditure that you need. So the money, to bring the money to the table is an expensive thing. So you've got to get your money cheaper as well. And you get cheaper money if your risk is less.
Just going back, Alan.
Yeah.
What costs a third though? Is that the turbine or the...
Turbine.
It is, okay.
What is project financing? Is it the complete cost or just a part of the capex?
The project financing is effectively the investment banks or the if it's a utility doing on its, or an oil company who are doing a lot of this now, doing it on their balance sheet. How much do they have? How much is it costing to take that capital? So it's the interest rates or the risk associated. If it's insurance, project financing includes insurance as well, by the way. So it's the insurance premiums they're paying to insure what they're doing. It's the cost of the coupon, the interest rate on the money that they're borrowing, if they're borrowing it, be that external borrowing, which tends to be the way it is, as opposed to the original wind farms that were developed certainly around the UK and Europe. Most of those were done on the balance sheet of big utilities because they could afford to do it. When you get bigger machines, more expensive, it's about £3 million per megawatt to install a turbine. So it doesn't take long before you've gone from 2 megawatt machines to 15 megawatt machines to see what the impact on the capital reserves of the people who are developing this could be if they did it internally, i.e. on their balance sheet. So what they do is they take it off the balance sheet and they bring third-party finance to the table, and the cost of the finance can range, you know, what's interest rate still 5% or something. So it will be probably 3 percentage points above the LIBOR rate. So it'll be about 8% they'll be paying for that. But then you've got the insurance premium as well. So the cost of finance is not insignificant. So the lifetime costs, when you project out 25 years, you know, what's it going to cost? There's a bit of that, you know, a bit of guesswork involved. But now, as time marches on, the guesswork becomes less because the data is there. Operations and maintenance, 28% of the cost of running of a wind farm will come from O&M. The foundations, typically 18%. The big steel structures, there's a big SEER on Teesside are building their factory for foundations, and that's going to be great for the region. There's going to be a lot of jobs in this. Electrical infrastructure, cables, JDR Cables are building a brand new cable plant on the Port of Blythe. We talked about project financing. That doesn't stop. You've got to keep paying it over the life of, you know, they don't fund this and then walk away. You're paying over the duration of that asset's life. And the turbine as well, you know, the turbine is not insignificant as well. You know, it's around about 23%. So lots of cost. This varies over time, but these are the averages that you would see. And as the industry changes, you know, these numbers will change as greater levels of sophistication come into these different components. Yeah, sure.
Have you ever considered about decommissioning costs?
I'll come on to that, because the decommission, I'll come on to it. Hold that thought. Right, just to give you some comparison as to where things are, approximately, with levelized cost of energy of different technologies. So tidal, which is still relatively in its infancy, there's not that many. They're very expensive, functional, but £250 a megawatt hour is typically where it's at. Onshore wind is sitting at about 45 pounds a megawatt hour, and there's been very little in terms of extra construction of onshore wind in England, plenty in Scotland, not so much in England over the last 5 years. That's about to change, one thinks. As you can see, offshore wind has tumbled from being around about there about 10 years ago to being down here now, just less than 50. The government set the price for the new nuclear power stations at around about £95 a megawatt hour. And coal, which we don't have any, we have one coal-fired power station, which is very rarely used in the UK now. But coal was sitting at around about £55 a megawatt hour, coal-fired technologies. So you can see, no subsidies anymore. Very, very, very cost competitive because the supply chain has matured and people have become more attuned to the risk they're dealing with. And so the risk has been priced down over the years as opposed to being embedded forever at a particular high level. I'll come on to, I haven't forgotten about decommissioning. I'm coming on to that. I just want to give you a little bit of some pictures to make life a little bit more interesting. These are two farms that I've had some dealings with over the years. I'll start on the right. This is the Blythe Offshore Demonstrator, which is something we got permitted and we got the money for around about 2010 at Blythe. I was working at what's now the Offshore Renewable Energy Catapult, which was then the National Renewable Energy Centre. And we came up with this idea to have a demonstration site so that technology providers could demonstrate their technologies. The original thesis didn't work because nobody wanted to demonstrate their technologies in open forum. So what happened was the site was ultimately sold to EDF, the big French utility to operate as a test site for itself. So there was a commercial deal done. It still is. England's, not UK, England's only demonstrator as an equivalent in Aberdeen. Only offshore wind demonstrator farm. It's got, look, more than 2 megawatts. That's 8.3 megawatt machines. So that's where this went to. After 2, it went to 4, then it went to 8. So there's 8.3 megawatt machines times 5. So there's just over 40 megawatts installed. The site is permitted for 99.9. That was for a reason, because if you went to 100, you had to go through a different permitting regime. So we went for 99.9, expecting the turbines to be 4 megawatts. By the time it's built, they're 8 megawatts. So you've got the ability to put fewer turbines on that site if you're going to do it with today's technology. So there'll be another line of 5 which goes further out into the ocean, and there will be that'll be a floating offshore wind park. 5 turbines, demonstrator, EDF are building it out. So floating is it's the next frontier. It's where they don't just float away, they float in a locus. So they're tethered to the seabed with catenary chains, and the turbines move around like that. They don't fall over because physics is compensated for. There's control systems and there's all manner of different buoyancy mechanisms at play. These are fixed bottom, so they are drilled in. They're not actually drilled, these. There's a big concrete bucket which actually keep these on the seabed, which is called gravity-based foundations. That's what they've got. But usually they're monopiled, or there's a jacket structure which is fixed to the seabed, which is the case in Block Island, which is off Rhode Island in the United States. It's now, this is slightly out of date because there's two offshore wind farms operating in the United States now. This is the first one. The other one is a 2 by 6 megawatt machine off the coast of the Carolinas. It's the forerunners to what's going to be some very big wind farms developed off the coast of Massachusetts, called Vineyard Wind, which is one of the things I've been involved in. But this is slightly different. These are 6 megawatt machines. So this capacity installed is 30 megawatts. GE Wind, which has a factory in upstate New York, it's Halyard 150 is the design there, whereas here it was MHI Vestas, it's now Vestas, which those turbines were produced on the Isle of Wight. That was commissioned in 2016. This was in 2017. This is Ørsted. This was EDF, as I said. Jacket foundations there, gravity-based foundations here. This is 3.8 miles offshore. This is about 30 meters of water depth, 40 meters of water depth. So not too dissimilar farms developed in 2 different parts of the world for the purposes of testing the next generation of turbines. So these things are very important to do so that you can de-risk the turbine design. So I'm summarizing remarks, then I'm coming on to decommissioning. Okay, so what have we covered? Well, we've had a bit of a whistle-stop tour of a few things. The production system, we've talked about the interplay between technical and financial aspects of offshore wind. We've looked at categories of risk. We've looked at the rise of maritime security, and I've steered clear of going too deep there because there's lots of sensitivities around what's going on, and you'll never get the security forces to tell you what's going on, but it's stuff going on. We talked about levelized cost of energy, and we've sort of majored on that because it brings everything together in a neat way. And I'll give you a little bit of an insight into 2 operating demonstrator farms. Right, now we're coming on to decommissioning. So there's a whole value chain which exists in offshore wind, which starts with the permitting. So you have all the science which is required to look at what's happening in the ocean environment, environmental impact assessments, bat surveys, bird surveys, flora and fauna surveys, everything. You get the decision, the green light, that takes you into the construction phase. So you get your final investment decision, then you're free to construct. You construct it, you commission it, your operations and maintenance cuts in because you're in warranty. You've got to do what you've got to do. You then go out of warranty and 25 years on. So the value chain the value is being added as we're going across this chain. And then you come to the end of the 25 years, your permitting, in theory, has run out because you're permitted for a period of time, consented for a period of time. See, I've got American, you see, I can't help it. I keep saying the American phrases. I shouldn't really. And then you go into the big question, what next? So what can you do? Well, you can either keep going. So you push that bathtub curve out a bit further. So you say, right, okay, how have we done? What's the data telling me? Is there any more mileage in this? Now, to get that re-permit or the permit to be extended, you have to prove to the permitting authorities that nothing has changed. Okay? All you're doing is extending the time because the assets are up to it. They're capable of being extended. They've been performing well, da-da-da-da-da. That's one option. The other option is that you say, right, okay, 25 years have passed since I started this. What's changed? So the turbines have gone from 2 megawatts to 15. So I've got, let's say, 200 turbines in this site. 200 turbines means 200 turbines need to be maintained. So can I make life a lot easier for myself from a maintenance cost point of view by shrinking the number of turbines but increasing their size? So when you get a permitted site, you get two things. You get the number of turbines because you have the impact assessment of that number to deal with. You also have to conform to height, noise, all of the parameters that we talked about earlier on need to be considered when you get your permit. And if you go for a re-permit, then you may be changing some of those parameters. The height will definitely have gone up, for example, which means the radar impact might be different for the local airport. You might want to have that radar upgraded. You also got the footprint in the ocean might be different. So the question then becomes, can I use the existing permitted zone adequately? Can I get a permit which is going to give me another 25 years by putting fewer machines onto this area, but I get more power production from them because the bigger machines times the number is a greater number than 200 times whatever the machine size was at the beginning? That's a question. The third thing is we take the whole thing down. We decommission it. So when you start on this journey of the whole financial thing about offshore wind is you have to put a decommissioning bond in place at the beginning of your development. That money sits in what's called an escrow account for the day down the line, 25 years down the line. Obviously, it gathers interest and everything else. It's just in a bank account. That money is to be used to decommission those assets, take them down, or it's going to be used to re-permit. We haven't really seen any of this yet with wind farms which have sufficient stature to make this the start of a trend or not. But what we will see is individual sites being assessed for their suitability for one of those three options. But my personal view is that you've taken all of this cost, you've taken all of this effort to get a site permitted. Well, everybody in the world is wanting green energy, security of supply, bearing in mind what we've just discussed. How secure is the supply? But that's another question for further down the line. Will deconstructing a wind farm serve those objectives? And the answer is probably no. So you're more likely to see the first two, in my opinion, at this stage, you're more likely to see the first two scenarios being played out than you are the last one. So the decommissioning bond, which is put in place at the beginning, will serve its purpose by either rolling forward as a decommissioning bond for the next wave, or it will be used to help de-risk the farm of the future to come. But the stakeholders are all involved. Everything I had on these slides today starts to come to life again because the stakeholders, the permitting authorities have all got a vested interest in now. Well, wait a minute. This is now it's now a 15 megawatt machine. It's now sitting, 150 meters in the sky. What it was previously, it was 70 meters in the sky. We need to do all of those surveys again because what's going to happen if this protrusion or these protrusions, because you're going to have quite a few of them, start to have a negative impact on the environment in terms of birds, bats, flora and fauna. So we're off again on the journey. So it's just a re-permitting exercise with a new permit wrapped around it for the next 25 years. That's the cycle that we're in. But we haven't got to the end of the first 25 years yet, really. There are two original turbines, offshore wind turbines in the UK, were at Blyth, Northumberland, 2 times 2 megawatts in the ocean, and they were decommissioned 2018 because the gearbox was shot. They were workhorses, and they served the purpose in terms of demonstrating that you could put. And we learned a lot from that. We learned about cable erosion. We learned about how not to do things in the ocean environment, saline entrainment into the gearboxes, everything. So they served the purpose in terms of the knowledge base that I showed on that diagram as well.
So in terms of decommissioning, do you think that the wind industry is actually learning from the oil industry in this perspective? Because the oil industry is currently in that phase of decommissioning, but what I've noticed is that many companies are now, rather than relinquishing their license, so they've got to commit to decommissioning, they're just extending the life of the field. Or other companies are coming in to buy those older fields off to relinquish companies from having the decommissioning problems, because they can extend the life, or looking at potentially converting it to a CCS site. So I wonder if the wind companies may well be changing hands, whereby somewhere like Ørsted may not want to bother with the decommissioning or resiting new wind turbines, and will sell that asset off to another company. Is that happening? Or?
No, it's not happening yet, but it's a real possibility. If you look at what happened onshore, utilities were the ones who, on their own balance sheet, created a lot of these onshore wind farms, and they decided about 10 years ago, I would say, maybe 12 years ago, to start selling off the smaller sites, because those specialist providers, private equity funds, got a nice assured return for the pension funds, and others were piling in to buy these things, and a little mini industry was created around due diligence on existing, say, 10, 15-year-old assets. And the idea, of course, is that you get to the end of their normal 25-year design life and you push it out. And so it's the same dynamic underway in onshore wind, and we're seeing that transfer to offshore wind and oil and gas, because the industry now, because of floating offshore wind, that's effectively oil and gas technology in terms of how you stabilize a rig floating in the ocean, how do you stabilize a turbine floating in the ocean. So that thinking is coming in, and especially as the expense of floating offshore wind starts to pick up, the oil and gas majors are the ones with the money to do this. The utilities, it's even beyond the utilities to do this, really. Or they put it into a joint venture and they progress it, de-risk it, and the more liquid party buys the other party out. And that tends to be the way things go. I mean, Ørsted, the Aspen sites, Ørsted have floated a number of offshore wind farm percentages or ownership rights when they've been permitted and when they've been partly or when they've been partly constructed. And they relinquishes capital to do other things. So that's it.
Topic, sorry. I don't know if it's concerned you or not. I was wondering what it takes, how do you calculate the cost of production from wind turbine? Like, in the combined cycle power plant, we have two components. One is the fuel component and the variable volume component. And the fuel component is dependent on the heat rate or the efficiency of the turbine. In the case of wind turbine, we don't have that case.
Yeah, you do. I mean, it's exactly the same as it's a turbine. I mean, it's a power station in the sea. So you've got the capacity. It's called capacity factor it's called capacity factor in turbines as well. But it has typically been 30% in wind. So you see, a 10 megawatt machine is the theoretical rating of the machine. The reality of that is you'll get 3 megawatts out of it over a year.
Because of varied wind speeds.
Wind speeds, efficiencies, production of noise, and what have you. So the capacity factor is now increasing with the new technologies up to touching 50%, which is absolutely amazing that the turbines become that efficient. but there's no cost of the fuel. It's free.
Yes.
So that cost component vanishes, and it's all of the costs that I showed on those slides, which make up the cost of operation, as it were.
Okay.